Well, you know how when you go to a concert, there's usually some kind of second-rate warm-up band and before the main attraction? Well, I'm the warm-up band today. And this is just to set the stage. What I'll talk about is first, what is astroinformatics? How did we got here? How does it fit inside the data science in general? I'll talk about two important aspects of it, machine learning and its challenges and visualization its challenges, and then two emerging technologies that will push us further along both of those directions. Say a few words about methodology transfer in data science and conclude. And who is she? She's Urania, the muse of astronomy. And we obviously need a muse of astroinformatics. Well, so what is astroinformatics? It's essentially an amalgam field of data science, which in itself is an amalgam field of many things, engineering, computer science, statistics, and whatnot, and astronomy. And virtual observatory became essentially, oops, what happened? Okay. Virtual observatory, which started circa 2000, essentially developed into the worldwide grid of astronomy, became our data commons. But it didn't do much in terms of knowledge discovery tools, which were developed by the community. And so main motivation behind starting astroinformatics as it was is to really provide those data knowledge discovery tools and include a much broader community of astronomers, scientists, both as users and contributors. And it's just like other X-informatics, bioinformatics, and so on. It is really a bridge between astronomy and what's now called data science, had the different buzzwords in the past. And just like data science, it has many different components. So it would really contain all manner of aspects of computer science, engineering, data analytics, and whatnot, architecture, hardware, and whatever. And to me, the most interesting part is what I would call data analytics, which in itself has a bunch of components. Machine learning, important one, and algorithms and statistics and visualization, numerical methods. And all of those are something that we use in order to discover knowledge in the data. All these things talk to each other. And this is essentially data science in microcosm. But it's useful to always take pieces of data science that are dedicated to a given field like bioinformatics or astroinformatics and give them that one catch-all word. Those are not sciences in sense of the physics or chemistry and astronomy. They're really composites, a different kind of science, nevertheless necessary and very useful. So I always like to review what are the most important trends that are happening today, not just in science, but in general. And the most obvious one is the exponential growth of data, both data volume and data rate, because it's derivative of exponential, and it happens on Moore's law timescale because the technology that produces the data is described by the Moore's law. So we're seeing some interesting things happening, that we're moving from data poverty in the past to embarrassing riches of the data. And from data sets that are done and stationary to data streams that constantly grow and data that get amended and recalibrated and so on. And so you pretty much have to move fast. You have to analyze things in real time or you will never catch up. And because in data analysis, most of the expense computationally is in moving data from here to there, you really only want to go through the data once. So even stationary data sets become data streams. It's all in distributed resources, and the focus changed from ownership of data, which was the important currency of the realm in the past, to the ownership of expertise. There is just so much data out there, excellent data, that you can be first-rate observational astronomer and never see telescope in your life. And that's new and different. So all these challenges happen not just in astronomy and not just in science, but in all other aspects of modern society, in commerce, in industry, in security, and what have you. And so the question is, what's new? Why is this not same old stuff that we've been always doing only with more data? And there are three things that I can think of. The first one is that for the first time in history, we cannot look at all of the data. That human bandwidth is not sufficient to take a look at data. So we need the data mining technologies, things like databases and data access and what have you. The second thing is that data are much better. They contain a lot more information that people who took the data were intending for them. Sloan is an excellent example of this. And so that enables profitable data mining, but it requires really good data analytics tools. And the third one, which I think is really interesting, is that the growth of data complexity is such that we can be pretty sure that data contain structures, important, interesting structures, that are simply incomprehensible to human mind unaided by something, which is why we need to move towards collaborative human-computer discovery as collaboration with humans with the machine intelligence. Pepe Longo, who unfortunately couldn't be with us, always points out that all laws of physics have up to 3 variables. And the universe is not fixed on 3 variables. There could be laws of physics that have 300 variables in them. We just never found them because they're too complicated for us. So why did astronomy get this way? Well, there are a lot of stars. This is Gaia image generated from their catalog. Couple billion stars, all manner of properties. It's a fantastic data set. It really is prime example of why astroinformatics is needed. And so, of course, there are many, many surveys going on in past, and then we now have synoptic sky surveys that cover the sky repeatedly. And so we're generating these highly dimensional, fast data streams, and this is what requires some interesting new tools. Another important part is data fusion. We need tools so that we can combine data sets, and because there is knowledge present in some data, it's not discoverable unless you do data fusion, like a multi-wavelength region. And the universe looks different in different wavelengths, and different physical processes contribute energy in different parts of the spectrum. So whichever one you choose, you have a biased picture, and you have to look at all of it in order to really get a more complete idea of what's going on. The same thing about time axis, not just one epoch, but by looking at multiple snapshots, you can start seeing processes that you would never understand with just one exposure. So there is data fusion in time domain as well. And something that I never can be stopped, being amazed about, is that theory has undergone fundamental transformation. That now we do a lot of theory that's not analytical, that you have to mimic inside the machine what nature does out there by using simple laws. But if you can stare at Newton's law of gravity all day long, and you will never be able to guess what happens when you start merging galaxies with tidal structures and what have you. And all complicated things, all complex phenomena are non-analytical. They simply cannot be predicted. And in fact, in case of Newtonian gravity, it's been proven by Poincaré 100-odd years ago that there are no analytical solutions for more than 2-body problem. So this is a very profound thing. We're doing these numerical simulations not because we're too lazy to solve 200 billion differential equations, but because there is no analytical solution. And this is the only thing you can do. And so then, theoretical statement is a data set, output of simulation. And those data need to be matched with real data. And so data science is not just about actual measurements or observations as astronomy, it's also about interpreting theory. And so this is, I think, really a very important change, paradigm shift even, that I think most people haven't grasped yet. So here is my simple way of encapsulating history of data-intensive astronomy, and to my never-ending amazement, astronomy has always been on the cutting edge of these things. We started using digital detectors as soon as they became apparent, and so CCDs or digital correlators. And this is when we started getting into the exponential data growth, because digital detectors were governed by the Moore's law. And so then we quickly went from megabytes to gigabytes to terabytes and so on. And at every stage of that, we had to introduce new technologies. First, just image processing on megabyte scale, then pipelines, then databases, and the virtual observatory came in, and machine learning to try to digest all the data. And now we're looking seriously at machine intelligence and other things. So astronomy has been always very proactive in using the latest of the technologies in order to help us deal with our data richness. Something that I think, again, is worth pointing out is a lot of our data comes from surveys. And usually, we do segmentation of images and have sources. And for each source, we measure a bunch of numbers, hundreds or thousands of numbers. And those form feature spaces, multidimensional data spaces. And sometimes, some of these features are immediately interesting. You can just work with raw data, like colors, find quasars. And sometimes you need to actually fold them with additional data like distances or theoretical models and so on, and then you look at physical parameters. So the way you explore this vast data space is by employing the language of feature spaces in computer science. At some point, most multidimensional measurements are reducible to this format. And this is where the interesting things happen. Well, so in order to do this, we need tools, and that's where machine learning comes in. And in fact, I would say this exploration of feature spaces is probably the sort of central problem of all data science. And machine learning is our tool to go about it. And so you can do a variety of things. You're looking for clusters and correlations and outliers and what have you. And there are a number of interesting challenges. And in particular, I would say scalability with number of dimensions, which is what algorithms are really get to be very expensive as you increase dimensionality, and visualization, which could be a really fundamental limit. So just one slide about machine learning, about classification, clustering, outliers, which is what most of it is. Well, there are several hundred algorithms or data models, as people talk about, and it's never the case that one size fits all. You can't just blindly choose to use neural network or what have you. And so there are pros and cons. This is where the skill of a data scientist comes in, understanding which methods are good for what. And you have to experiment and find out sometimes. So here is my cartoon of what's our generic or generalized problem. You have this high-dimensional feature space, which is here as pseudo 3D cube, and it's covered with data with some distribution, noise or random, or could be correlated noise or what have you. You may not know what it is. And there could be gaps, there could be inhomogeneities, which are real or artificial, so on. And somewhere in this vast multidimensional noise field, there is something interesting. And something interesting could be a correlation, it could be clustering of some sort, or something like that. And so you're supposed to find it. So we're essentially looking for islands of lower entropy in this multidimensional ocean of data. This is essentially an impossible thing to do with present-day technology, with the kind of data we're talking about. Brute force is not a good approach. So the skill comes in finding methods that will lead you into the right portion of the parameter space, into the right set of dimensions, and discover things that are statistically significant in some sensible manner, and not assuming Gaussian noise, but what the real noise is. So this is sort of the challenge in front of us. Another big challenge is the uncertainty quantification. And by this I mean taking into account all of the aspects of the data analytics process. We all know how to propagate errors and how to do Monte Carlo and the square root of n, but every decision you made, every choice of algorithm, every choice of workflow, everything brings in an additional uncertainty because it's a choice. You don't always know what's the best. And so amazingly, there is no established formal framework today that will really produce complete uncertainty quantification for complex processes. Here example is just climate prediction models. And what they do is they run a whole bunch of different models. And they take the upper and lower envelope, and that's your uncertainty. But there is a whole manner of hidden things in there, not just numerical errors and Poissonian errors, but all these choices of analysis. And this is a really interesting challenge that a lot of people are trying to cope with today. Now, the second important challenge is with visualization, which is an essential part of the entire data analytics process. From the first look at the data to see what you got, the data cleaning, to look at the geometry, to figure out what kind of algorithms can you use, what can you trying to find, and looking at intermediate experiments, finally understanding the results, and then presenting those results. At every stage, you have to be able to visualize data. And the problem is that data are highly multidimensional, hundreds or thousands of features, and how do you visualize that? This is, I think, probably the single most fundamental limitation of data science, because we're optimized for 3D space, and we can maybe, with various tricks, see up to 10, 12 dimensions of data space encoded in a pseudo 3D display, but that's it. So you have to do clever dimensionality reduction and feature selection, and then experiment with it and see what's hidden in that space, because you really do not understand anything unless you're visualizing it some way. That's the bridge between data and your intuition and understanding. And this is really a problem, because all simple stuff's done. Now we're getting into this high, very information-rich, very complex data sets. Unfortunately, most of the traditional data visualization ends at 1 or 2 dimensions. And if you have multi-dimensional set, well, you look at a whole bunch of one-dimensional trends. That's not the same thing. That essentially ignores all of the mutual interactions of these variables. And if you have structures in highly dimensional spaces and you project them down to any plane or any axis, you're smearing information. You're losing knowledge. So the premium is in finding ways to visualize effectively as many dimensions of data space as you can at once. So we do this. There is essentially always mapping between your data axis and what you may want to call visualization axis. And some of them are obvious, like XYZ positions. We can play with sizes and colors and transparencies and shapes and glyphs and so on. And you can actually encode as many dimensions as you want. But you start losing track after 7 or 8, maybe 10, up to 12, which is what different experiments have shown. Now, different ways of encoding quantitative information have different precision relative to the human perception. The most precise one is the positions. We're evolved to be able to spot what's where. And then it goes down this axis, but it depends on exactly what it is. Now let me illustrate this with you. Originally, I thought color is a really great way to encode information, because we see in color, 256 RGB levels, you can play with that. All right, so let me test you. Here's grayscale and the rainbow. Stare at the grayscale. How many different levels of gray do you think you can distinguish by looking at the picture? And it's not 256. It's not even 50. Come on. Any guesses? The answer is 7. Except for some people who are unable to do even that. That's pretty bad, huh? So much for the grayscale images. What about colors? How many colors do you think you can see, distinguish? It was chopped that rainbow. You guys now know it's not going to be 256, right? Yeah, well, amazingly enough, the answer is also 7. So it turns out color is a lousy way to encode quantitative information. And people who do human-computer interfaces and design and so on actually know all about this. It's just astronomers and other scientists don't, right? And so there are different tricks. What you can do with colors, how do you encode, how do you balance lookup files and so on. Okay, well, go back to dimensionality. So this is typical diagrams you see in papers, and this is from a 6-dimensional data set of colors of quasars, from optical to infrared. And for 6 different axes, you have 15 different 2-dimensional plots. You can look at all of them. You see something interesting is going on, maybe 2 clusters, maybe 3 clusters, and so on. But if you start encoding things, if I can hit, here we go, start plunging into the data space, we use XYZ positions and RGB colors and sizes and shapes and transparencies of the data points, suddenly the data become alive. It's much easier to instantly grasp the geometry of the data space and examine individual data points. You see instantly that there are outliers. What's that red cube doing in the middle of it? You'd never be able to see this in traditional ways. And you can do a lot better than that if you can actually immerse yourself in such a space, because it turns out that triggers human intuition and understanding way better than any flat screen display, which is where virtual reality comes in. So our colleagues at JPL have built a virtual Mars from imagery from the rover and orbiters, and you put the headset on and you're standing next to Curiosity rover on Mars. And you can walk around and you can have perspective and look at where the different rocks are and whatnot. And they tested people who drive the rover. They normally look at panoramic photography, and decide, oh, this looks like an interesting rock, we'll go there. And so they divided them in two groups, and one group did that in a standard way, the other one did it in virtual reality, and they asked them to estimate distances and positions of different rocks. People doing it in VR were 4 times better in accuracy of saying what's where. And today, Curiosity rover is actually driven in virtual reality every day. Okay? And they start to use this for planning spacecraft orbits and what have you. We've also been doing a lot of experiments of how does this apply to these scatter plots in multidimensional data spaces, and this is work in progress, but there have been some cases where there's absolutely dramatic improvement in time to insight. That it takes, from days or months to analyze something down to minutes or hours in some cases. And some things you simply can never see in traditional data analysis because you need this ability to expand axes in different spaces. So fortunately, virtual and augmented reality are becoming reality and highly affordable thanks to the games industry that invested zillions of dollars in it. And most people now see it as the natural next progression in the way we interface computers, from punch cards, to terminal, you type things, to swish and point and all that. And now we will interact with machines in some 3D space for which we're evolutionary optimized. And also it's a natural way to collaborate. It turns out to be very powerful, where people can collaborate in virtual reality and it's almost as good as really being there. And even if people can be in different parts of the world, they share the same virtual space. So here are just some snapshots of different ways of people looking at or analyzing data in VR. You can collaborate very effectively, applying machine learning tools. So essentially, humans are talking to each other and they're also interacting with the data and interacting with machine learning in a much more rapid fashion than you can do using any traditional desktop environment. Okay, well, where do we go next? Beyond machine learning, machine intelligence. Well, we use machine intelligence in the form of machine learning and some other things already very extensively, essentially at a growing number of different steps of data analytics. We've been using things to classify stars and galaxies since early 90s, and there's more all the time. So you need AI to help you clean the data, find problems with the data, then find genuine outliers, and so on, find where the data are, and even design codes that will, in principle, could be bug-free, even though humans may not understand them. Well, here is my brief history of machine intelligence. It starts, of course, with Alan Turing, of Turing test, who wrote that paper in 1950. In 1960, somebody you may have heard of, J.C.R. Licklider, who was a DARPA project manager, and you can thank him for the existence of the internet, wrote this paper called Man-Computer Symbiosis. And it was amazingly visionary. He just didn't have the technology to do it. It's only today that we're getting stuff. And then things really started expanding in the 90s. Astronomers, I'm proud to say, started using machine learning to analyze data in the early 90s. Google, of course, came about in 98. And so every time you use Google, you're talking to machine intelligence. Now you can literally talk to it. Major milestone in 2012, because of course we use computers to look at pictures of cats. And now things get to be really interesting. So you probably know about AlphaGo, that in 2016, computer became Go champion. Now, before that, computer became world chess champion in 1998, and that was predicted. This will never happen. Machine will never be able to, beat human in such an intuitive game. Well, it did. Kasparov discovered that. But Go is much more complicated game. Well, now computers can play Go. And then, a year later, another code was only given rules of the game, nothing about strategies or anything, invented its own strategies and beat the previous champion computer from 2016. Now that is amazing, right? The machines are thinking in the ways that we cannot or do not. And that is the important part. We want machine intelligence not to do the same thing we do, but to do things better that we cannot do or in different ways. And depending on whether you're optimist or pessimist, you can find this wonderful or scary. I, for one, wish to welcome our new machine overlords. And don't say we haven't been warned. Hollywood warned us about this, and Elon Musk as well. But actually, I am an optimist, and I think just like any technology in the past, we're using it not to replace humans in any way, but to enhance our ability or liberate us from doing some chores to do something else. I like to look at pictures of cats. Right? And so I think the path is really towards building genuine symbiosis with this new alien intelligence that we created on planet Earth, which really is alien, doesn't think like humans. Hopefully. On the other hand, if we had human self-aware super intelligence today, it may take a look at news and decide the best thing to do is to exterminate humanity, and you'll be kind of hard-pressed to argue with that. But okay, finally, a little bit about data science methodology transfer. Some fields are ahead of the others in this evolution from data poverty to data richness, from traditional methods to the informatics methods. And we all deal with same problems. So the question is, can we effectively transfer knowledge from one field to a different field, save people making mistakes? And the answer is yes. So let me just show you a couple examples of this. So in astronomy, we look at, in time domain astronomy, we have surveys that find transient events. Then we deploy some sort of machine learning to figure out what it is. Then hopefully, at some point soon, we'll have automated decision making to decide which things are worth following up with what. There's, of course, feedback loops, and then get data with big guns. Somewhat similar to this is work that Julian Bunn at our center has been doing with Caltech seismologists. They figured out a way to use cell phones as earthquake detectors. Each cell phone has an accelerometer. Individually, they're too noisy. They have a cloud-based algorithm that first figures out which cell phones are at rest, like not walking or driving, then averages those signals, and turns out to produce more precise earth-shaking maps than Southern California seismograph network, which is pretty good already. And then, of course, they can send alerts to subscribers that earthquake's coming, because it wave propagates at the speed of sound in the earth, and ostensibly internet propagates to the speed of light. Of course, we know that's not true. But I thought this was really a spectacular reuse of some of the knowledge that they developed to analyze data from Large Hadron Collider and apply it in a completely different field. Ashish Mahabal has been working with Dan Crichton at JPL in building what's really a virtual observatory for cancer research. Early detection research network. It's an aspect of cancer research about biomarkers for early detection, which is very important. And it uses, or rather reuses, technology developed at JPL called ODT, or object-oriented data technology, which is open source, and was developed to make data systems for space missions, and has been since reused in all manner of different contexts: medicine, space science, earth science, defense, and all manner of other things. So this, I think, is really spectacular, because medicine is facing phenomenal data avalanche with precision medicine and individual medicine, and it's completely unprepared to deal with this. They do not have computational data culture. They yet have to grow it. That will take a generation or two. So they have to import people who know how to do this from other fields, just like biology did 15 years ago. And if we can help do something useful like this, well, that's way more important than analyzing data from any sky survey. Another little project we did with neurobiologists at Caltech is looking at clinical diagnosis of autism. And just to make a long story short, basically what they do is they give patients a questionnaire. Does this face look happy or sad or whatever? And so people, do multiple choice tests. Each question counts the same, usually like 30 or 50 of those. Each hospital had their own questionnaire. So all total, about 600 different questions they were asking people. So by using techniques we developed to analyze data from sky surveys and also from Large Hadron Collider in feature selection, we found out that 6 questions contain all of the information and give essentially a perfect diagnosis. Everything else was just spoiling things. It was just adding noise. And so this was a trivial thing to do. We're limited by the data, but it just shows that you can really transfer the knowledge from one field to another. Neurobiologists are a smart group of people. They have some really sophisticated algorithms themselves. We can learn from them as well. And now we're thinking of working on brain imaging and things like that. Okay, so I'll wrap up here. I'll leave a little bit of time for discussion. So these are my key points. I will not read you the bullets, but essentially all science is changing, scientific methods evolving, and it's driven by very rapidly evolving technology, fastest evolving technology in the history of the world. That the key points are here. It's not data science is not about data. It's about discovery of knowledge in the data. The 2 key components of this is machine learning, leading to artificial intelligence, and data visualization in complex data spaces, where I think virtual reality coupled with machine learning will help. And those methodologies can be shared between different fields. So this is really what data science aspires to do. And just like there is one statistics, not different statistics for biology or physics. What's astrostatistics? Well, I don't know. But rather there'll be only like one methodology of data science that everybody's going to learn. And of course, the same things are important in every field, a modern world, which guarantees employment for everybody here who learns these things. And we're already seeing substantial brain drain of talent from universities into the commercial world, because anybody who knows how to do anything with the data, they need that desperately badly. Okay, so I thought we'll stop here, open the floor for questions. Go ahead.